Okay. Okay, now maybe you can hear me. Sorry for the problem, but yes, we had some problems before. I hope that everything now goes in the proper way. If you can't hear me again, yeah, I'm sorry for that. But now maybe the problem is resolved. Okay, sorry, I can't because of time repeat. So yeah. Yeah, yeah. Maybe quite faster than before. So yeah. Okay. Yeah, just the key points. Sorry for that. Okay. How can I say? Yeah, if you, of course, Simulink is a built-in of MATLAB, and for that, you can, if you want to create a background of MATLAB, you need, of course, go to MATLAB Academy, okay, .mathworks.com, and there you can just launch MATLAB Onramp, and in a handful of hours you will be able to work with MATLAB with its environment and of course coding. Okay. After that, I need to skip some, of course, slides. Here, the Simulink overview. You can work with. I mean, Simulink is useful if you have a model, if you want to work on it, if you want to understand, and this is the point, how it works dynamically. Okay, so in a ever-changing situation where you have some inputs and some outputs, and you want to understand how it works during all the phase. Of course, Simulink is really important because if you can understand how your system works dynamically, you can much better answer respond to your design phase. So if you have some problems, you can work on it directly before creating maybe physical model. Okay, so if you need to create, if you want to understand how your car works, um, and if you want to understand how your cars work, how your car works, and you haven't created it yet, then you can work with Simulink, understand some the problems they may occur, and then fix them, and then create the physical model. In such a way, you can just save lots of money, of course. And this is a powerful tool of Simulink, and every kind of engineer should use it for yeah, it's for his work. Okay, so this is an example. You can model your, for instance, we are modeling here in the image wind turbine. Okay, and wind turbine is a big physical model, and if you want to create it, you will need to spend lots of money. And in this way, you can just understand how it works really easily and in a cheap way. Okay, this is our some examples of application of Simulink. Another one. Okay, Simulink Onramp. Okay, you can just download it inside MATLAB. Okay, so you can download and install Simulink Onramp from the MATLAB File Exchange, and then launch MATLAB and open Simulink. And after that, I will show you there is a place called a line called Simulink Onramp. You click on it and you start the Onramp indeed. Okay, Simulink, of course, is a block diagram environment. As you can see here, there are blocks, lines, is created as so. Is a model you can model, simulate, and analyze multi-domain system. This is our, for example, domain system here, and I'll show you another one in the next here in the next slide. This is a multi-domain system example. Okay, aircraft longitudinal flight control. We have some inputs and of course some outputs, and this is our system. It might be complicated here, but in such a way it can be seen as an easy way to understand a model. This is just a model indeed of a system. And more from that is a platform for model-based design. So you need to create a model. After that, after having created a model, you can just understand the system. Okay, skipping. This is our environment. This is it's a blank sheet, and it's the workspace. You can just add blocks, lines, connect them, and create your model. Here on the top left hand side, you can find the new. You can create new files, new workspaces. You can save them, and here in the library you can find all the blocks you need. Here, this is the library. There is a long list of blocks, and here you can find all the blocks. They have little images on there just to understand what they do, and of course their names. And yeah, you can find everything, and I show you that there is really everything. Okay, so let's start with Simulink Onramp. Okay, here we have, okay, now what you are seeing, what you are watching is just MATLAB. Okay, so you're now in MATLAB with the command window, the folder, the workspace, etc. On the top, you can find, of course, all of the dots, important dots of MATLAB, and here you can find Simulink. Okay, so you click on it, and you'll be displayed in such a in a moment. You'll be displayed the first page, the start page of Simulink. Okay, here you can create you can open your model. There are some the blank model, okay, white sheet. Here the library and the project, etc. Here on the left hand side, you can find Simulink Onramp. Of course, you need to download it previously, and after that you can just click on it and open it. Of course, my Simulink Onramp is already done because yes, I've done it previously, so it's completed. And but don't worry, we will go on together inside it. Well, just waiting. Yes, of course, my computer is now calculating for Simulink, MATLAB, and it's open also OBS for the direct on YouTube. So yeah, we need just to wait. So, okay, it's open. In a bunch of minutes. Yes, okay. As you can see here, there is a list. I'm not sure that you can see properly. I don't know if I can zoom in. No, unfortunately. But I hope that you have opened it on your computer. Okay, there is a list, of course. There is a Simulink Onramp, and it's divided in capitals here. Okay, chapters. and we start from the overview, and we will finish in conclusions. I think that I will skip just a bit, just to have some more time before after our on ramp. But okay, you need to know that of course um, Simulink is an important device, an important tool for your career, but because you can really simulate everything, and I'll show you now an example of an application. Okay. Yes. See. Yeah. Turn up. Ah, okay. Okay. Uh, let's try. Maybe yeah. I mean, the gain is actually at the top in on OBS. Okay, advanced audio properties. Ah, yeah. No, there is a. Okay, let's try it. I have yes. For instance, now I am 1.7 decibel, but much more than that. Okay, okay, we will see. Okay. Well, I'll try to speak louder then. Okay. Thus, I had yes here the I don't know why, but every time I try to open the Simulink Onramp, all the windows will be open in the first display. But okay, let's try to understand the environment here of our system. Okay, so as you can see on the left hand side, you can find the tasks of our on ramp. In the middle, you can find the system. Okay, for instance, here we have mass spring damper system. I see. No, sorry. This is another example. Yeah, this is for the velocity, the acceleration. I mean, there is of course the drag force for a point which goes in the air, maybe in the air, and this is the our system indeed. So to start, if you want to create no, well, I skipping. Okay, this is just text, and this is our equations, and those equations are indeed the counterpart of this system. Okay, so as you can see here, there is a G for gravitational force, and here we have it, and here the mass, and this is the gain for the mass. There is an integration because the acceleration is the derivative of the velocity. So here we have the opposite, the integration. Here the output of the velocity, and of course the square and the drag force coefficient. Okay, so our task is just to connect the velocity to just our signal assessment. It's just for on ramp. We don't have it in the normal Simulink, but to display what is going on. Okay, so what is going on with for the velocity? This is our solution. I need to connect the velocity here. Of course, as you can see, these lines are just a signal, okay? The signal for the velocity is this one. The signal for acceleration is this one. And the connection here is just a way to display, okay, the solution. Now submit or just run. You can run or submit. If you submit, of course, it runs. And in a second we will display if we are good, right or wrong. Okay, everything went well. Okay, what else? Our task now is to double click on the block named drag force coefficient and change its gain to 0.1. Connect the velocity signal to the new signal assessment block and click submit to run and assess your model. Okay, so as you can see here, you can just click on it, on that block, on this block, and each block means something. For instance, we are asked to double click on it, to the gain of the drag coefficient. We will be displayed a little box, and here you can just change the gain of the drag force coefficient. We are asked to write here for 0.1. Click OK. As you can see here, the drag coefficient is changed to 0.1, and yeah, we need to connect the velocity to the signal assessment and submit. In a second we will be displayed the solution. Okay, this is okay, and to the next task. Of course there are other further tasks, but we need to skip on to the next section. Okay, so I go quite quickly here. As you can see, there are some boxes. You have seen some boxes in the previous example. The box means that you can just elaborate your input, as here displayed, and of course this box will show you an output. Okay, so this is how it works. You inlet a signal and the outlet will be another signal. And here an example. So you can just connect the two blocks and create a signal between them, just to click and drag the arrow. Okay, so if you want to, we will be display a suggestion if you align two blocks. And yeah, this is another example. You can also click and drag between any two ports. Okay, so like that. And if you want to start the simulation, okay, so it will be start calculating. The Simulink will start calculating, and it's just with the button run. And let's go on. Okay, we have another environment of Simulink Onramp with the tasks here and the assessment there, and inside, of course, the sheet where you can work on the workspace indeed. Okay, so what is asked is to open the library, okay, browser by clicking the icon in the toolbar here, and click on the Simulink sources library and locate the sine wave block. Okay, so we want here to create a block. It's easy. It's you can just open the library and yes, looking for the sine wave. Yes, yes, it it's requiring some seconds because yes, of my computer, because usually is much more faster. Okay, in the other page, of course. Okay, this is our library. You can find everything here, and but we were searching for sources and sine wave. So here, drag and drop like that. Now here, and with the space bar, you can just fit better the workspace, and just connect it. Okay, submit, and the solution will be actually this one, as you can see here in an orange line, and our solution will be blue. Okay, don't waste time, we can just go on. Okay, this is our solution. Okay, so double click on the Simulink Canva and type math function. Okay, this is another way to input new blocks. You don't need to go to the library browser, but you can just double click here and search for math function. Here will be displayed a math function. Okay. Um, and this is another way to search inside the library, but of course here there is a point. Okay, you can just double click. We've been asked to search for the square. Okay, so this is another way to, and it of course the image changed, and this is another way to create new blocks. Okay, not searching for the library, but just double clicking and search the name, if you know, of course, the name. Okay, connect the output of the sine wave. This output of the sine wave, you can that connect it to the square, and then connect the square to the signal assessment. And the solution, of course, changed as before, because we are squaring, okay, elevated to the power 2 the sine. The solution is okay for Simulink, so we can just go on. Use the Quick Insert menu to add game block from the Simulink Math Operation library. Activate the Quick Insert menu by clicking once canvas and typing a block. Okay, so you can just click here on the Canva, on the workspace, and just write for gain here. And with double clicking, you can always change the gain here, like 0.05. Yeah, this is displayed okay. You can just open, and here you can just create the connection, just moving the gain, and the output of the gain is this red line. You can connect it in the signal assessment, submit, and hope for a right solution. The solution is okay. Next, and next section. Okay. So quiz. Which of the following is true about Simulink signals? Okay, signals contains data that can be constant or time varying. That's true. Okay. Signal flow is bidirectional. No, because there is an input and an output, a before and after, and we have just just an arrowhead. So big direction is wrong, and the signal are represented by lines with arrowheads. It's true. Okay, correct. Happy me. And this is another one. Okay, so how can you understand what is going on inside your signals? There is a block for that, just to display the solution, the last solution of this simulation, or all the solutions you will face during the simulation. This is an example. We have a simulated signal here and a low-pass filter here. So only the lower frequencies will be displayed. So go directly to the next example of this filter, and yes, we will have our exercise. Okay, so we have the filter here. Hope that you can see it. And here in the column tasks, okay. The first task is to add a display block to the model. Connect the unconnected signal to this block. This is the filter's output. So I want to understand what is going on at the end of our simulation. So this is our display block. Okay, just to try to zoom in. Okay, I haven't connected it, and now it's connected. Try to submit or just run, and at the end we will show you it will show us the number. Okay, after 30 seconds, you can see here on the top there is the seconds. Estimation, you will display this number, and it's okay, so you can go on. Select the display block and replace it with a scope block. What scope block? The scope can display all this section. Okay, so we can just search for scope and click on it, drag it, and connect with the solution. Okay, click the block to open the scope window, then run the model. Okay, so you can just run. You can just open the scope, and after that you can you'll be displayed in a matter of seconds. The scope. Okay, is right there. As you can see, it is a black grid. You can just run it. It will be displayed the solution over our simulation. Okay, it's working. And here we have our solution. And unfortunately, yes, it's yellow over black, and this is our okay. And yeah, but I'll show you that we can start a smooth sine. After that, okay, connect. We play it, and the solution is right. Next section then. Okay, so this is really useful. Okay, now we want to connect scope to signals. Okay, so we can branch the signal level noise signal. Okay, this is this. Okay, this is our signal. This, and we want to understand how we want to filter the noise and just leave the base signal. But to compare them, we want to compare the base signal filtered noise. So here the noise signal. We can branch it and connect it to the scope with the right click, the right of the mouse, and then we can just double click on it. Yes, it's more fast. It's faster. We can. What will be shown is the comparison between the signal filter and the another signal and one. Okay, so if you want to understand which is one, we can just open the legend. And okay, so as you can see here, of course, the name of the legend is depends on the name of the signal. So we have the noisy signal, which is named, and this is L1. Okay, and so it's just a filtered signal. So we read this solution. Okay, so we can see it. As you can see, thus the scope is really useful for this kind of situations. If you want to compare your signals and you want to understand what is going on. What is on in your dynamic. Okay. Label the other signal connected to the scope as filtered signal. So this one, so we can move just to more space. You can just click and filtrate signal. Just press enter. Add a legend by toggling view legend from the menu bar in the scope window. Okay, so you can just click on it. We have the legend, so we can just run, and at the point of the place of add one, which we displayed before, now we have the filter. Okay, so now we can just submit. Hope for a good resolution. Okay, perfect. So next task, we can just close this and wait for the next section. So here we have a video, and yeah, I'll try to show you. If I hope that the volume will be good for this, but I'm not sure. Not in fact. I can hear you. But yes, in this video you can just see that you can display simulation thanks to the scope, and it's really easy to understand what is going on in this dynamic. You can just zoom in, you can span, you can move, and of course you can stand the number of inputs, and you can work really quickly. Thus, this is really easy. You can split the inputs and split them separately, and yeah, you can add the legend, move, change the colors, etc., etc. And this is our scope block. Okay, so. We can just go on with the basic of algorithms. Okay. As always, yes, we need to just wait. Okay. And here we are. Okay, as you can see here, we have our ramp. Okay, so is an input, of course. I can just zoom on it. Okay, and for our tasks, okay. So first task. Compute the square root of the ramp signal, okay, by adding the square root block. So double click on it, really easy. Search for square root. There's here the suggestion, and here we have our block for the square root. Okay, so you can just drag and the should be created. You can see here it's easy to calculate every kind of operation. Okay, and yes, hoping for a good resolution. Yes, perfect. Next, okay, what's up? Add the constant block. Okay, we can just add the number. Okay, to the model. Change the constant value to 3. So double click as usual, just to yes skip constant, and yes. Here our block. Okay, so to change this to 3, so you can just click it, double click 3. Okay, connect to the okay, you can just put in here to the assessment. Okay, hope for a good result. So here we have a constant, okay? So we can just work with everything from inputs we change in the definition to the constant number. Okay, place that block the model, provide the difference, root 2 times t minus 3. Okay, so, really easy, subtract. Okay, what's going on? Yes, okay, we have it. What else? Now we can just create an addition, I mean a subtraction, sorry. I created one. Okay. This is our subtraction. What I'm going to connect is 3, okay, with minus. So over before 3 there is a minus, and with the plus, this one. Connect them to the signal block, and will be display the right solution. So what I'm doing, I'm just adding this root 3. I mean, I actually root. So really easy to write equation. Okay. To amplify the previous result by a factor of 2. So you can just multiply the result with a gain. Okay. Really easy. Another way, gain. Okay, I have a gain. We can multiply that and to the report and then to the assessment. So I multiplied the result of the block of 2. For yes, okay, good result. Next section. Okay, so what we have done here, the mathematical operations, and of course we can do it for logicals and for conditional statements. It's quite important. We can't skip it. So yes, we can open it. Okay. So, with input, you can see here the same way. More, also another data of input is written that the frequency is 1 rad per second. Okay. Here are compare to 0 block. Okay, the compare to 0 is something that in the input we have a number, okay, a signal, and the output will be a 1 or a 0. 1 for true, 0 for false. Okay, so easy. To course, yes, here the compare to 0 block. Okay, add compares to 0 block to the model. Change the operator to greater than operator. Okay, so double click. You need to change to greater than. Okay, and connect the sine wave such that the block outputs 1 when the input is greater than 0. Okay, so as you can see, I can just connect the sine wave to the block. Okay, as you know, the sine wave can go from -1 to +1. Half of the period of sine will be true, and the solution is indeed this one. So for half of the period we have true, then we switch to false, and then to 1, which is true. Okay, really easy. So we work with logic, and also copy and paste the existing sine wave block and changes its frequency to 2 radians per second. Add a compare constant block to the model and connect to the 2 rad second sine wave and the assessment block. Okay, so you can click Ctrl C with copy, Ctrl for pasting. So we can change here the frequency to 2 and second. So add a constant to the model and connect it to this to the 2 radians per second. So another copy and paste. Okay, and we can just connect. Okay, set the parameter that the block outputs 1 when the signal is greater than or equal to 0.1. So double click on greater than or equal to. Sorry, I had a mistake. I don't need to compare to 0, but to compare to a constant. So I went wrong. I need just to write compare to constant, which is another one, which is not a compare to 0, because compare to constant is why don't you is quite slow, because yes, because of my computer indeed. So again, compare to constant. Hope for I click in the right way. I'll show you. Oh well, something went wrong. That's a problem with the. Okay, so yes, I'm wrong because I put the wrong here, the wrong block. Now I have compared to constant. Okay, really easy. Double clicking here, and with the greater than equal to, the constant is not 3 but 0.1. Press OK, connect it, and connect to the signal assessment. Okay, submit. And what it will be displayed is just the right solution. Oh, 4 indeed. Okay. We are calculating, as you can see here. Okay, there is a application. Okay, results are good. Next task. Okay, add the logical operator block of this model. The default operator is AND. Use the comparison and connect the signal so that the signal assessment block outputs 1 when both of the previous statements are true. Okay, so you can just export. You can just write a logical operator here. Now you see that's an AND. Okay, the output will be 1 if all of the inputs are true, and it will be displayed 0 if one of them is true and the other false, or both are false. Okay, so here, okay, here connect, and the other one is that. Connect to the signal assessment, and will be displayed the right solution. So only if both of them are true, it will be displayed 1, as in the figure. So in this part of the 1, after that 0, and after that again 1, only if the both the solutions are true. Okay, other practice, nothing left. Okay. So there's a way to obtain information about blocks. You can just press on help, or here we have the description of each block. Okay, if you don't know what a block is for, you can just read on it. There's a little description, but if you want more documentation about that, you can just click on help, and you'll be displayed this page for that. Okay, so you can just skip on it and go directly to the project. Okay. Okay, now we want to project a cruise control. I'm sorry, not a cruise control, but an automotive performance package. Okay, so let's go directly to the simulation. We will see that if the velocity of the car is more than 100 km per hour, or it's more than 35 km per hour, but the lateral acceleration of our system is greater than a value, okay, we need to insert a certain mode on the car, okay, so the car can understand what is going on during the driving. If there is something wrong, it can switch between two modes, a mode for that kind of situation, and a mode if everything is going in the right direction, for the other situation. Here we have just the sensor data. We don't need to bother for that. We need that the first block, the output will be speed and the lateral acceleration. Okay, so please don't be afraid of that. It's just the out. But then, what is asked to us? Add an abs, okay, but to take the absolute value of lateral accelerations, abs of the lateral acceleration. So I write abs, okay, here we have abs, and we can just connect to the lateral acceleration output. Okay, what else? Nothing. Solution. Hope for right. Next. Okay, so I will create our set. Okay, if speed is greater than, or the speed is greater than 35 kilometers per hour, and lateral acceleration greater than 3 meter per second squared, we need to use the mode 2. Otherwise, the mode 1. Okay, so this is our pseudocode, and we want to implement it on Simulink. Okay, so add 3 compared block to the model, set their condition to 135 and 3. Okay, copy and paste, and paste. Okay, so for the first one, we want that or equal to 100. Okay, for the second, we want or equal to 35, and for the third, we want to greater than or equal to connect blocks to their appropriate signals. Okay, so for instance, so we want the speed greater than 100. So I need to click on that, but there's no 35 kilometers. So I need to branch with the right click of the mouse to 35. Okay, and then lateral acceleration greater than or equal to 3. Okay, so this is really easy. Remember, okay, submit. We don't need to connect this somewhere. Just click this last. Okay, so we created the if. Okay, add a logical operator block to the model. Use the default. Okay, so with and. Sorry, I should search for logical. So logical, really easy, but sometimes I went wrong. Okay, so we create the AND logic port. Okay, and what we need to connect: the speed and the lateral acceleration. 35 if it's true, and if it's true, this the output will be 1. Connect the output of the AND block to the signal assessment block. Okay, so this is 1. As you can see, the sensor data will be displayed a sort of dynamic example. Okay, so the car here is moving, and the output is the speed and acceleration, which change during the simulation. Okay, so add the second logical operator block to the model, but this time is OR, so I can just copy the logical operator and sorry, copy, and just you can just check there's AND, OR, NAND, NOR, XOR, and XOR NOT. So there are lots of them. Okay, with OR, and we need to write speed for over than 100 and the solution for the end here. The solution of OR is so we create a sort of code for if else. As you know, in MATLAB there is the if else condition, and we wrote it on Simulink as well. Okay, so is add the logical statement replicate here. So if something like that happens, we need to use mod 2, else mod 1. Okay, really easy. So we need to create a port which is called switch. Okay, the switch operator. As you can see here, the switch operator. Okay, so the first input is the mode 1. So if something is true, we use mode 2, and this is use mode 2. if something is if this one is wrong, else use mode 1, and else use mode 1 is the third input. Okay, the middle input is just the if. Okay, so this one goes in the second port. So I need to connect the OR here. Okay, but for the mode 2 and mode 1, I need to just create some constants. Okay, the first constant is this one. Copy and paste for the first, for the second. The value of the constant will be 2. Okay, and for the mode, we use the mode 2 if this condition is true. So we need to connect it in the first input. Then input be the third, sorry, be the second one. Check to understand if we done a good system. Okay, everything went in the right direction. Okay, next to that, and next section. Okay. Okay. MATLAB function block. Okay, so you can add function from method. Okay, in Simulink because of course they are twins. They can collaborate together, and this is an example. So in this block, as you can see here, there is also the little image of MATLAB. You can create a function with inputs that are those ones, and the outputs those ones. And okay, I can just go directly to the example because in the image I think that you can see really properly what I'm showing. It's a little tiny, and maybe there will be displayed better. Okay, so maybe I can enlarge a little bit this workspace. I just wait for the tasks and then work on. Try to zoom in. Okay, so here is the image of MATLAB. The input will be sine. Okay, so here we have a function, elaborate sine, and the output will be just the power. Of course, the input is called delta h. Why? Because the input will be delta h, and the delta h varies with the sign. Okay, the output will be just the power. Okay, I will show you that we need to work on the function. Okay. Okay. The MATLAB function has been pre-populated with values of the constants. Double click to open the MATLAB editor and then add the equation such that delta H is the input and the turbine power is the output. So we need to write this equation inside the function. Double click on it. And yes, in a moment, unfortunately, I think that we can't put in a good way I think you can see properly the function, but I can just describe it. The function have as output the power and as input the delta H. We have some numbers like power coefficient, density, rho, the area of the turbine A, small type stuff. Just write for power equal to 0.5 times C times rho times A times I don't remember again. That's 0.5 rho 2 times G times the abs of delta H. 2 times G times abs of delta H to the power of what? Let me see. To the power of 3 over 2. So 3 over 2. Okay, so we have written the equation. Hope for having written it in the right way. After that, I can just connect the output of the power here. So, as I said before, the input will be the sine, which is delta G, as as sine as delta G, and the output will be the power. Okay, so good connection. Okay, submit, and we can just work with functions of MATLAB. So really, really, really easy. So if you have a function really complex and you can't display, and yes, this is the ordinary differential equation, the counterpart addition. What we're gonna see in this the next example is that we can work with continuous system or the discrete system. We will work with the discrete system in the really next example, and after that the continuous one. Wait for open Simulink Onramp. Yes. Okay. Disaster. Add the sine wave to the model. Double click on the block and change the sample time parameter to 0.5. Note that icon changes to indicate that it is discrete. We change the sine wave, which is an input, from a continuous system to a discrete one. Okay. See, yeah, some things, but sine. Okay, so we can just zoom in. Double click here. Here. Now it's 0. Switch to 0.25. Press OK. Note that the icon changes. Indeed, it changes. It changed, and as you can see here, it's discrete, not more. If you like at a continuous sine wave, but now, okay, and we need to connect it to the signal assessment. As you see here, the sine is not more continuous; it's discrete. And as you can see, there are steps, like little steps. Okay. This is a way of course to work with. Okay. Discrete system. Discrete dynamic system is a model of a system current state x of x k based on current and or previous states. The day, this one, is used to create of one step. Okay. So we want to work with one created. As in the video, is useful because if you want to understand an okay. So if you want to create a day, then you can understand what is go previously and what is going previously and what is going afterward. Okay, so connect the delay to the signal assessment. And we have the solution. Okay, so we the unit they created is decimal -1. Okay, the position 4 of the signal. And what we want to do is to on a side of unit to identify them as the current or previous states. Use x of k here. X of k minus 1 for the second. So we've delayed. Submit. Oh well. Okay, compare x of k and x of k minus 1 by connecting both signals to a scope. Okay, turn the legend on to identify the signals. You will see that x of k minus 1 has the value of x of k delayed by 1 time step. So I can create a scope. Okay, I can connect it with the branch, the x of k and the x of k minus 1 here. Double click on it. Have its own and there's also f k minus 1 delay bar. Here s of k yellow and s of k minus 1 and the solution is right. That's good. Next. I can just let it go and double click the unit delay block and set the sample time to 0.5. Run the model and use the scope to compare the two signals. Okay, I will think the sample time. If you can see, I will show in a second. They usually have a sample time of -1. That means that sample time, okay, 1 for binary, and if you want to change the sample time to 0.5, for instance, you properly add a sample time. Okay, so it extends that. Now it must delay for 0.5. So this is the previous one. Now and the simulation will be shown again. As you saw, zoomed the this of one but of you. Okay. Okay. So it right. Next. Okay, so okay, there from this time there are all other examples. Okay, we go directly to the summary of it. Well, let's try to say something more of that. So if you want to create the delay, you can just use a unit delay block. So if you have x of k, if with a unit delay x of k minus 1, you can just work on it. Okay. So for instance, here we have this example. Okay, this is written as big. Arrange the equation so that most threatened state is on the left hand side. Okay, so if you have an equation and there is the unit and the unit delayed on the left hand side, you need to work as to free the x of k and the u of k, for instance, on the left hand side and everything else on the right side. Okay, so if you want to create a delay, if you want to write the equation, you need to create a delay as well. How many delays? There is the delays of x and the delays of u. Okay, so we need to add two delays. Okay, so in Simulink, you need to add two boxes. Okay, one for two blocks, one for u of k, and the second for x of k. After that, and this is the step-to-step solution, you can add everything else. For instance, here I need to add an add block. Okay, so there is another connections just to write the equation previously displayed. So here I need to add the u of k minus the u k minus 1, and here we have all of that. Okay, so there is the k minus 1 as of k minus 1. plus the u of k minus the u of k minus 1. So this is actually the equation described in Simulink. Okay, after that, after creating the connections, you can just work for the time step wanted, okay? And this is how to... il microfono mi dice che vada a Dio. Sì, non so... Hai un feedback? Mm. Ma il video c'è? Ora non lo so se mi sentono. I changed the microphone. I don't know. Let's say a gain of 50. No more than 20 gain of decibel. Now I changed the microphone. This is the microphone of the computer for OBS. Want me to switch to the the break Sheen? Andrea? Oh. But l'audio mixer mi dà che il microfono è altissimo. Cioè, mi sta dando proprio... Sì, sì, si muove proprio la voce, cioè la barra dei decibel. E tra l'altro adesso gli ho messo un gain di 20 e va sempre in zona quasi arancione. Really? Little voices or just a low voice or just more? Please give me a feedback. Yes, of course, there is also a delay, so I need to wait to I need to get your feedback. Okay, so maybe I just need to switch. Okay, let's try like that. After that, you'll tell me. Okay? Okay, let's try to talk of that. Okay, let's say we want to write the Newton's law of cooling, okay? The equation for for the temperature. To do that, we need to add a constant block to represent T0. Okay, so constant here, and this is our T0, which is in Kelvin. So we are asked to write here 300 Kelvin. Okay, and that's okay. After that, add a subtracts block to create the expression T minus T0. So okay, and we need to add the constant will be in minus, okay, and the other one is for T. So okay, so I created this subtract, and we can just submit. Okay, that's good. And we need to add gain block to create the expression minus R T minus T0. So we need to implement the gain parameter R minus R. So double click. And now what we need to do is that we want to implement the variables of MATLAB. As you may know that you can just add new variables in MATLAB. If they are written inside MATLAB, you can just call them like that. I wrote R. R is inside the workspace because yes, the Simulink Onramp has a workspace for that, and R is our number, is our variable, and I call it minus R. This is our gain. As you can see here, there is written minus R. I connect it to the. I try to zoom in just to let you see clearly that we have an subtract, a minus R, okay, and that's it. So we can just submit. Is good. Now connect the two signals representing T dot to create the equality. Connect the temperature signal T to the signal assessment block. Okay, so what we need to do is that the minus R, which multiplies this subtraction, is equal to T dot. So I can connect this gain to T dot. Okay. Like that. And this is our connection. Okay, so I connected T dot with that. So I created the equation. But I'm asked to connect the T, okay, to the signal assessment. So I can just branch with the right click on signal assessment and then submit. Here we are. Okay, so we created an equation, as you can see here. But of course, we want to open the block parameters dialog to the integrator block and set the initial condition. Okay, so you can just create an initial condition for the equation. you just click here in this page for the integrator, you can just decide the initial condition, the tolerance, the state name, etc., etc. For us, the initial condition is 320, and this is where we want to start. Okay, if you want to submit, there in the right hand side of the screen, you can find the evaluation of the dynamic, and in the equation, in the diagram, you will find that we start 320, and then the temperature goes to 300 because which is T0. Okay, this is our dynamic. We can just go to the next section. Okay, so the summary for us is that if we have an equation, I think that you can't see it, but the equation is yes, a differential equation. You can just leave on the left side, on the left-hand side of the equation, the higher derivative, and at the other end of the equation, all of the stuff left. Okay, so you need to evaluate how many derivatives you have from the second to the first, to the first to the I see the v, which is the non-derivative value. After that, you calculated the number of integration you need to do. There are 2 of them, so you can just create 2 blocks. The first integration from v dot dot to v dot, and after that another integration from v dot to v. Okay, to the signal indeed. You can just create all of the stuff you need to create the equation, this equation right there, this one, okay, 1 over c, which multiplies that stuff, which is a subtraction, and here we have the subtraction for the first, and then the gain 1 over c for the second. And yes, if you want to change the initial condition, as always, you can just double click on the integration. Of course, you need to understand which integration you want to change, and this integrator is the one who has the initial condition on the signal you want to study. Okay, so really easy. Calculate the number of differential equations, create the integration as the number of the differentiation, and then create all of the equation with gains, with subtraction, addition, etc. And then you create your system. Okay, really easy. After that, we have a quiz, yes, of course, but we can just go on with something else. Simulation time. Okay. Yes, there is a place where you can. There is a chapter for this Onramp which shows you the simulation time and how it works, but we can just skip it and try to have an example. Okay, we will gonna have an example of a thermostat. As you know, our houses are warmed, are heated during the winter, the cold winters, and we need a controller to understand how to switch on, switch off the heater. Okay, so we have our system, the dynamic system, which is our house. We have this house, and outside can be cold, can be hot, can be warm, can be cool. Okay, it can be windy, and depending on the situation, there is different temperatures, and the house, our system indeed, need to be heated in such a way. The controller can understand it. Okay, so For instance, I can set a point, for instance, 22 Celsius degrees, and if the temperature is lower than it, we need to switch on the heater, and otherwise, if it's more than the set point, the temperature is more the set point, we can just switch off the heater. Okay, so there is different ways. For instance, we can just switch on, switch off in this way, or we can just change the controller. For instance, if the delta t is quite slow, quite small than the set point, we can just switch on the heater, but a little bit. Or if it's really cold and we want to warm the house, we want to switch off the heater, and all the power of the heater is used to heat the house. So there are different ways of control the heating system of the house. In this way, of course,